Hi everyone, thanks for watching my presentation. I'm Parvin, master student at Concordia University in Montreal, Canada, and my supervisor is Professor Arash Mohammadi. Okay, let's go to the slide. Okay, our paper's title is Non-Gaussian BLE-Based Indoor Localization via Gaussian Sound Filtering coupled with Wasserstein Distanc. First of all, we know that the indoor localization has many applications in our daily lives. For example, in the smart buildings, it helps to reduce the energy consumption, or in the firefighting, it helps to monitor the firefighters into a burning buildings, or in the hospitals, it helps to monitors the patient or help the patient to find the correct rooms between so many rooms in the hospital, and also has application in the airport, for example, monitoring the employees, wheelchairs, and the people with disability. So how can we do the indoor localization? As we know, we cannot use the GPS for indoor localization because the strength of GPS is weak in the indoor venue. So instead of that, we use the Wi-Fi signal, BLE, and a smartphone sensor for indoor localization. But our focus in this paper is the BLE. First of all, what is BLE? BLE is the abbreviation of Bluetooth Low Energy, which are the sensors that receive the Bluetooth signal from the phone or send this Bluetooth signal to the phone. And we show the strength of this Bluetooth signal with the RSSI, or Receive Signal Strength Indicator. In general, we can classify the methods of indoor localization via RSSI into the four main groups. The first one is trilateration. That for using trilateration, we need to have the distance of the user to at least 3 BLE sensors. Another method is fingerprinting, that uses the fingerprint of small zones into the indoor venue and estimate the location of the user to one of those zones. The third method is filtering, like the particle filter and Kalman filter. And the last one is the tracking, that use the history of the location of the user to predict the current location of user. But the most important thing is that we can optimize and combine this method together to find the algorithm with high accuracy for location estimation. As we know, the RSSI signals are prone to the noises, fluctuation, and fading, which this causes to the low accuracy. One of the general methods for removing this noise and fluctuation is using the Kalman filter. But Kalman filter is an estimator for linear state space model with this assumption that the noises are Gaussian. But we know that in many cases, our noises are not Gaussian. What should we do? In this paper, we propose the Wasserstein Distanc Gaussian sound filtering, or the WDGSF, to approximate this non-Gaussian noise with a mixture of Gaussian model. Our proposed algorithm has two main phases. The first one is the offline and the online. During the offline phase, we divide our indoor venue into the small zones. For example, here we can see this square zone, and measure the RSSI value at each zone, and model the RSSI value of each zone with a Gaussian mixture model. After that, during the online phase, is that we should predict the zone which the user is located via pattern matching. For example, here the user is walking into this path, and we should predict that user is located at this zone. Okay, let's go for the offline. As I mentioned in the previous slide, in the offline phase, first we measure the RSSI signal from all of the beacons for each zone. So, for example, here shows the RSSI matrix for zone L. Here we can see that, for example, each column shows the RSSI receiving from NAB beacon, and we measured in a train sample RSSI from each BLE. After that, we modeling all of these column vector via Gaussian mixture with this formula, which is the weight and the mean of the mu and covariance of sigma. So the next phase is online. We do two main steps into the online phase. The first one is that we applying WDGSF algorithm for two purposes. The first one for preprocessing or removing noise removing the RSSI value, and the second one constructing Gaussian mixture model of the online RSSI vector while the user is working. The second purpose is the pattern matching via Bhattacharya Distanc. So let's go to our formulation. We mentioned that here our nose is non-Gaussian. So at time step K, we receive this ZK RSSI from the NAB beacon. For noise removing that, we have the prediction and the update. In the prediction, we have this formula that XK consists of the YK, which is the preprocessed RSSI value, and delta YK shows the rate change of the RSSI value. For the update phase, we have the ZK with this formula, which ZK shows the received RSSI signal from the beacon, which include the noises. So YK shows the noise remove RSSI, and here shows the noisy RSSI vector. And as I mentioned, our noise is non-Gaussian, so we show that it's a mixture of Gaussian model. Let's go for our proposed algorithm. The first step is the prediction step. Here we did this one that in the previous slide we saw that XK is the removed RSSI and the change rate of the RSSI. The next step is filtering because our noise was a Gaussian mixture model. Here our likelihood function is also a Gaussian mixture model that its mean is ZK given K-1 and its covariance is SK that we calculated this by this formula, and the WK is the weight that we calculated that with this formula. The next step is collapsing or a likelihood function or PZK given XK in the previous slide. Here was a Gaussian mixture, but here we wanted to collapse that to just a single Gaussian to QZK given XK with this formula. For collapsing, we use the Wasserstein Distanc based Gaussian mixture reduction. We know that for Gaussian mixture reduction, we can use the Bhattacharya distance or Kullback divergence distance, but Bhattacharya distance and Kullback divergence distance doesn't consider the geometric shape of the distribution. Just try to optimize the gain information for the GMR. But the Wasserstein distance consider this geometric shape and try to reduce the cost of transferring one distribution to another distribution with lower components. So that's the reason that we use Wasserstein distance for GMR. So here until now, we have our likelihood function with just one single Gaussian. And let's go for the update phase. That here we calculate the Kalman gain, and here at the end we have this formula which we calculate the ZK given K minus 1 through GMR in the previous step collapsing. So at the end we have XK given K, which X is our um, clean RSSI value without the noise. And the last step is pattern matching. For pattern matching, we use two scenarios. First one is that we calculate the Bhattacharya distance between the online RSSI vectors, ZK, and all of the Gaussian mixture model of all of the zone and associated the zone with the smallest distance as the current zone of the user. This one. The second scenario was the applying weighted nearest neighbor, but with the weights of the inverse of the Bhattacharya distance between the online RSSI vector and the zone, the model of the zone. Our experiment setup. We measured RSSI value into a 4 meter by 4 meter room that we divided the room into the 64 zones, square zones, that the dimension of each zone is half meter by half meter. And we located 4 BLE beacons in the corner of our zone. For fingerprinting, during the offline phase, we measure 1000 RSSI vector at each zone. And for evaluation or test, a path trajectory is created, which shows by the black line. Okay, then we model the RSSI value at each zone during the offline phase with the Gaussian mixture with 2, 4, and 8 components. After that, applying Gaussian sum filter on the online RSSI vector and associating Gaussian mixture with 1 and 2 components to them. After that, we applying two-zone detection scenario based on the Bhattacharya distance for the on this online gym. Okay, here is our results. The first table shows the results for the first scenario, that was minimizing the Bhattacharya distance between the zones. That here we can get the accuracy of 62%. The second table shows the results for the second pattern matching scenario, or rated nearest neighbor for K equal to 5, and we can get the accuracy of 95% when we model our offline RSSI values with 2 Gaussian mixture, and model or online RSSI value with 2 Gaussian mixture. That accuracy of 95% is good. And here shows the or pre-processed RSSI value. The red one shows the original RSSI values with noise during the online phase. Green one shows this pre-processed signal by using the conventional Kalman filter with the assumption of the Gaussian noise. But the blue one shows the pre-processed RSSI signal by using or Propest algorithm, WDGSF, and as we can see, our Propest algorithm remove the noises much better than the conventional Kalman filter, which is shown by the green one. Okay, that's it. Thank you again for watching my presentation. I will be happy to answer your questions.